So this question deals with how to find the value of principal stress and maximum shear stress under the following condition. Uh, they have three conditions. First one is an axial load condition, second is a bending load, and third one torsional load. So in the question, it's a cantilever circular rod which is having a diameter 50 mm and 300 mm length. You have to find the value of the principal stress and maximum shear stress under these three cases. First one, an axial load of 20 kilonewton. Second one, there's a bending load is given 4 kilonewton, which is acting downward. And third one, a torque of 1.5 kilonewton meter is acting. So we have to find the principal stress and maximum shear stress on each of these three conditions. Okay, let's look at how to solve this one. So this is a given condition. We have length 300 mm, d 50 mm, and okay, we have to find the stressor at the critical point. That means at A and B, top and bottom. And the first question, first case is axial load condition. As you can see, it is depicted in the given figure. 20 kilonewton axial force, axial 20 kilonewton axial force is acting on that member, and I'm assuming that that force F1 will be that axial force of 20 kilonewton, and it has to be converted into Newton. We have to, because we have to get the stress in megapascal. That means Newton per mm square. So in order to get that, I have to convert it in Newton. So 20 kilonewton equal to 20 into 10 raised to 3 Newton. And it's a tensile load. As you can see, it's a tensile load. So we have these are all the given condition figure, and let's look at how to solve this axial condition. So first we have to find the axial stress. We know simply the tensile or compressive stress. The basic axial stress formula is force by area, or the force acting, or it could be said as a resistive force. In an axial condition or direct load condition, both are resistive force and applied loads are same. So F1 could be said as the resistive force or applied force, whatever it is, the same thing. So we have 20 kilonewton. Sigma D to be represented the axial stress. Okay, sigma D equal F1 by A. F1 20 into 10 raised to 3 by A. This is circular cross-sectional cylinder. So area of circle 5D square by 4. We have D 50 mm. Have to convert, you have to only put it in mm in order to get megapascal. So 10.19 Newton per mm square is the answer, which is the same as 10.19 megapascal. Okay, so for axial load condition, I mean, if it is a tensile load and if you don't have any other external forces, all the force will be uniformly distributed in along the length of the body. So here all the point in the member are subject to same thrust. I mean, this sigma d is, if you take any cross section, each cross section would have same thrust, same value 10.19. That is the condition for an direct stress, whether it is a compressive or tensile stress. Okay, that means axial stress. So, in order to get the principal stress equation, that force stress in the x direction sigma is this sigma d, because this is only stress in the x direction. Sigma x equal to sigma d, that is axial stress, that is 10.19 megapascal, and sigma y is 0. Under axial condition, there is no such stress in the y direction. Sigma y is equal to 0, and shear stress xy. So xy is also 0. Okay, so this is all about axial stress in axial load condition. Next step is we have to find the maximum principal stress and minimum principal stress, as asked in the question. So maximum principal stress is our formula. Okay, maximum to be designated as sigma 1, while minimum to be sigma 2. So this is noted in the case of an axial stress. Okay, it would change in bending and torsional. That representation would change. That we can see in the coming next part of the question. Sigma 1 is not to get maximum. Suppose plus sigma x, sigma 1 equal to sigma x plus sigma y whole divided by 2 plus root of sigma x minus sigma y whole divided by 2 whole square plus square x square. So why this is maximum reciprocal is the we have a positive notation between these two terms. On the other hand, for minimum stress, it is negative. So comparing this both terms, of course, the maximum stress would be sigma 1. Okay, simply apply the logic. So Maximum, not to get the maximum principal stress, you have to put plus, and minimum principal stress, you have to put minus. So sigma 1 and sigma 2 are 10.19 and 0 megapascal respectively in the case of, these are for axial stress condition. Okay. This is the maximum principal stress and minimum principal stress when the axial load of 20 kilonewton is acting at a body. Next, we have to find one more term, that's the maximum shear stress at this condition too. We have to find that too. So I have to find maximum shear stress too, right? So maximum shear stress is of the formula tau max equal to uh, maximum means which could be plus or minus. Right? It can be maximum in the negative and positive. So plus or minus root of sigma x minus sigma y the whole square, all divided by 2 the whole square plus tau square x y. This is the formula of maximum shear stress. It's not necessary you have to put that sign convention. You have to only consider the magnitude. So tau max is 5.09 megapascal. So these are the three. Uh, we have find the three terms: maximum stress, minimum principal stress, and maximum shear stress under axial load condition. Our next part is under bending load condition. Okay, let's look at how to solve the bending problem. Next case is bending stress condition. According to the question, there's a 4,000 Newton, or 4 kilonewton Newton is acting downward, which is causing the bending of the cantilever beam. So in each problem, first of all, we have to find the corresponding stress. We already find the axial stress during axial load condition. So we have bending load condition. You have to find bending stress. Okay. So bending stress is of the formula sigma b. It is represented by sigma b, which is m by z. What is m? M is the bending moment. So moment is simply the force into descent, right? So bending moment means that the force that causes bending. That means bending force into that length. Okay, that is F2 into L. Okay, I'm assuming that bending force to be F2 because I already call a axial force to be F1, right? So I am not writing bending force to be F2 and the whole length is L. Then Z is the section modulus, which is of this cantilever or cylindrical structure. Section modulus is pi d cube by 32. Okay, that denominator 32 is to go upward. That how we get 32 F2 L by pi d cube. So the formula sigma b equals 32 F2 L by pi d cube. Substituting, we get the bending stress as 97.78 megapascal. And as you can see, sigma d is 0. There is no axial load in this condition. So sigma d is 0. And below is the representation on how does an bending moment or bending force effect look like. It would bend, and top bottom will be having a area of tension, and the bottom it compress, right? So the inner fiber will be compressive, and on the top it will be having a tension. Now I got bending stress, so I have to find the principal stress at the uh, point A and B. So first of all, consider point A alone. So this is not to solve bending stress equation. It is not just like axial stress equation because you have to take the resultant. The axial gear condition can simply directly find principal stress, but in the case of bending stress problem, you have to find the resultant stress before finding principal stress, and that resultant stress is the combination of both axial and bending stress. So resultant stress at A, we know that's outer fiber where tension will occur due to bending. So formula of stress, net stress at A would be sigma D plus sigma B. That means sum of stress due to axial and bending. We already know there is the sigma D because they have told us to find separately. It is not a combination of both axial and bending, just bending alone. That's the second part of it. So that's how we find the net resultant stress at the point A. Similarly, point B would sigma D minus sigma B because there is compression. So that's why sigma D minus sigma B. So it will be minus 97.78 MA. So I got sigma A and sigma B, which is our net resultant stress at the A and B. Now I can find principal stress at the A and B, maximum and minimum. So maximum principal stress is the same formula, just like axial stress. You just substitute and you got sigma 1A. I have to give another notation because I have taken Resultant stress. Okay, sigma 1 97.78, while minimum would be 0. Okay, so I have to find the maximum shear stress too, right? We have to find all these three terms. So the term max A will be same formula, just like previous question. So that will be 48.89 megapascal. So I find the principal stress and the maximum shear stress at point A. Similarly, I have to find uh, next point B. Okay, principal stress at the point B. Next principal stress at the B, where sigma x will be sigma B, right? That bending equation, which is 97.79 megapascal, because I am considering the point B, which is negative 97.79, and sigma y is 0, tau x y 0. So similarly, just like you find at point A, I can find it the maximum and minimum principal stress, as well as the yield maximum shear stress at point B. Just use the same equation. All I have to do is change the numerical value. So the need to find resultant, or need to find stress separately at A and B, is because unlike axial stress, bending stress, it will have an effect on the structure of the body, because it will bend. So there will create a region of tension as well as compression. Okay, that will not happen in axial load, because that stress is uniform everywhere. But for bending stress, the bending load, it is not just like axial stress. So you have to find separately the principal stress at the point A and B. So we have solved the second part too. That is the bending load or bending stress case. Third one is the torsional load case. So let's look at how to solve that. This is the third case. We have a torque 1.5 kilonewton meter acting clockwise direction. So that is represented in the given figure. So just like we do axial stress condition and bending stress condition, we have to find shear stress. So shear stress is of the formula tau is equal to 16 E by pi d cube. Torque we have to convert into, we have the value in kilonewton meter, we have to convert in Newton mm. So multiply with 10 raised to x, 10 raised to 6. So 16 into 1.5 into 10 raised to 6 whole divided by pi into 50 cube. So the shear stress due to this torsional load will be 61.12 megapascal. So as you can already see, there is no sigma d stress due to axial load as well as sigma b stress due to bending load. This shear stress alone. Okay. So for torsional loading, the critical point will be out surface of the member, because the effect will be having on the outer surface. We have studied the theory that shear stress will be minimum or zero at the center of the body, but it will be having maximum at the outer part of the body. We have a circular cylindrical rod, so that maximum effective shear stress or that critical point will be the outer surface of the member. So next we have to find the principal stress. Here there is no sigma x. We all know sigma is equal to sigma d, right? And it is zero in this case. And the sigma y is also zero. But on the other hand, there will be tau, because it is directly causing shear stress because of torsion. So tau will be equal to tau xy. We have to remember if there is torsional load, tau xy will be that shear stress developed. So tau equal to tau xy equal to 61.12, and all other terms are 0. So you just have to use the same equation to find maximum and minimum principal stress and yield maximum shear stress. We got 61.12 megapascal at magnitude. So these are the three case, and how to solve this and find stresses and maximum shear stress problem. Okay.